response, let's see, what is this? This is not a good example. Let's say spring 21 is a good example, or spring 22 is a good example of the free response. I just want to work through the free response first. I said this is spring 22. It's a good example. You know, we have these problems on all the exams, but sometimes they're on exam 3 and sometimes they're on exam 4. But you'll see these. We've also done several examples in class. First of all, you're going to have a 2-lens system. I just copied these. I created different figures and different numbers and stuff. But you do this like a 2-part problem where I have P1 is equal to 30, F1 is equal to 10. I get that from here, and then I calculate Q1. So I have 1 over 10 is equal to 1 over 30 plus 1 over Q1. So that's 3 over 30, that's 2 over 30 equals 1 over Q1. So Q1 is equal to 15 centimeters. And then also M1 is equal to negative Q1 over P1, which is equal to negative 1/2. So when I draw that image, it's going to be 15 centimeters to the right, and it's going to be half the size of the original object. Oh, it should be a little smaller than that. At a distance of 15 centimeters, and it is inverted. Okay? Then I can find this distance just by saying 45 minus 15 is 30, and then that becomes my P2. So then I say P2 is equal to 30, and I go through the whole step again. I'm not going to do it all here, unless y'all want me to. Do you want me to? Okay, I'll do it. So I say P2 is equal to 30, F2 is equal to 15. So I say 1 over 15 equals 1 over 30 plus 1 over Q2. So just like I did before, now I'm looking for Q2. If I solve that, see 1 over 15 is 2 over 30 minus 1 over 30, so Q2 is equal to 30 centimeters. If you're having trouble with those fractions, let me know. I can help you with it. But it will help you to be able to do the common denominator and all that instead of having to do it in your calculator. I find you just make fewer mistakes. Then our M2 is equal to negative Q2 over P2. So that's negative 30 over P2 was 30, so negative 30 over 30, or negative 1. So that means that my image, the position of the final image, is this Q2. It's 30 centimeters to the right of the lens, of the second lens. And the total magnification is the product of these two numbers. So my total magnification is equal to positive 1/2. That's M1 times M2. So you have a 2-lens system. We've done those several times. No virtual objects, just real objects, and nothing like we did in the lab. It'll be more like this. Pretty straightforward. It's just two steps, really 2 1-lens systems. Probably the second question is going to be a little more difficult for you. Just the algebra is more difficult. And also you have to be able to identify the type of mirror or lens. This could be a mirror or a lens. The first one, definitely lenses, but this one could be a mirror or a lens. And you first have to identify the type of mirror or lens. You can identify it based on the type of the image. I have an object that's 3 centimeters tall, an image that is 6 centimeters tall. So my magnification is equal to 2. And it's upright, so my magnification is equal to positive 2. The only type of mirror that produces an upright, bigger image is a concave mirror, right? When I'm inside the focal point, I produce an image that's bigger, upright, and virtual. So my magnification is equal to positive 2, and so I know then that the center of curvature, C, is equal to 20. So F, which is equal to C over 2, is equal to 10 centimeters, and that's positive. So that's important, the type of mirror, because it tells us is the focal length positive or negative. In this case, it was positive. I think I asked the question, what type of mirror is this? This is a concave mirror. But that's also important for the focal length to be positive or negative. Now, our next step is to find the image distance. I know that the magnification, which is positive 2, is equal to negative Q over P. And 1 over f, which is 1 over 10, is equal to 1 over q plus 1 over p. So now you're going to have to do this to solve a system of two equations with two unknowns. And you do that by substitution. On this one, I find it's easier to solve this equation for q, just cross multiply. If y'all know what I don't think they teach cross multiplication anymore, but I say I can cross multiply, and so I get q is equal to negative 2p. I find that's easier to do it in that way. And then I take this, negative 2p, and substitute it in for q. So then I get an equation that's 1 over 10 equals negative 1 over 2p. I substituted negative 2p for q, plus 1 over p. I'm going to go and find my common denominator, which is 2p. So that's 2 over 2p. Then I solve that for p. So 1 over 10 equals 1 over 2p. So p, in order to make that equal, p has to equal to 5 centimeters. So that's my object distance. I'm actually asking for the image distance, though. And so I can plug in that 5 centimeters here. Q is equal to negative 10 centimeters. So the image distance is negative 10 centimeters. And the image to the left or the right, well, if it's negative, that means that it is to the right of the mirror. Okay? You're going to have a very similar question. Could be lenses. Could be, if it's mirrored, it can be concave or convex. If it's lenses, it can be concave or convex. Be able to identify the mirror or lens based on the type of image that's formed, and then be able to solve the system of two equations. There's a lot that goes into that. Okay, I know I worked through that quickly, but there's a lot. There's the algebra, there's sort of knowing the mirrors, there's a lot that you have to process to get that question right. So it's a difficult question. Julia? Yeah, the image distance is negative 10, and because it's negative, that means I have a virtual image, so it's to the right of that mirror. That's how I know it's to the left or the right. If it were a positive image distance, it would be to the left of the mirror, because that would be a real image. Okay? Y'all can do that for me? All right. Try to get it right. It's easier for me to grade if you get it right. If you get it wrong, it's much more difficult. So. All right, and then you're going to have diffraction grading. If you've done these a couple of times, you're probably okay with it. It's just really knowing how to do the equations. The first part is what is the slit spacing. By the way, y'all, if y'all can do number 3, you're going to have like 3 problems in the exam that are multiple choice that are basically the same. So you're going to have to repeat these, okay? So focus on this. It'll pay off in the multiple choice. That's true for the other parts, too, that you're going to have very similar questions in the multiple choice. If you don't know how to do the free response, master that first. Be able to work those problems, those practice problems on the old exams until you just don't have to think about it. That I know exactly what to do, exactly how to do it. So first, to find the slit spacing, I take the 10,000 lines per centimeter. I say 1 over 10,000 lines per centimeter. What's that? 10 to the minus 4 centimeters. And then I convert that into meters, which would be 1 times 10 to the minus 6 meters. So remember how to convert it. It will be centimeters or millimeters for that. And you will need to convert it into meters. That's true on the exam too, okay, to find the slit spacing. So then next, I want to know the distance from the central maximum to the second bright spot on the screen. I find pictures always help me think about this. So I can think about my diffraction grating. Look, diffraction gratings and double slits are basically the same. In fact, you can think of a double slit as just a diffraction grating, but just with 2 slits, okay, instead of the million or so slits that they often have. Anyway, I can draw my diffraction pattern. Has 2 orders. I want to know the distance to the second bright spot on the screen. So that is, I want to know this distance. I'll call that y. I need to find the angle theta. To find the angle theta, I first say d sine theta equals m lambda. That's 1 times 10 to the minus 6. I found that in the previous one. Sine of theta equals m. That's the 0th order, 1st order, 2nd order. So that's m is equal to 2, the second bright spot on the screen, times the wavelength, which was 400, times 10 to the minus 9. Make sure you don't forget this too, that you have to convert those nanometers to meters. Julia? That's right, the second bright spot. So I understand that there is, it actually looks like it's the third bright spot. That's what you're thinking, right? Is that what you're thinking? You were just asking. It looks like it's the third bright spot, but that first big central maximum is our 0th order. 0, 1, 2. Because it's mirrored on either side. So we start the counting on the first order, not on the 0th. Huh?
The middle of the biggest one to the middle of the second.
That's right, yeah. Okay? And I calculate this for theta. It's the inverse sine of 800 times 10 to the minus 9. That's the inverse sine of 0.8. I get 53 degrees. I think I did that right. Theta is 53 degrees. And then if I want to know y is equal to L tan theta. L is just the distance to the screen. That's 2 meters. So 2 tan of 53, which is 2.65 meters, 2.7 meters. Okay? Again, problems in the multiple choice that'll be similar to that. I know that's fast, but I feel like we've done that a bit. I feel like I'll be okay with it. Is that okay? Y'all can do that? If I gave it to you right now, you can do it? No. Okay, that's okay. But by Monday, you'll be able to do it. Juliana?
Can you go back like a little to where you do like the triangle with the theta?
Yeah. Yeah, so let me draw it bigger, okay? So this is a double slit. This is the distance between the slits. But again, same as for diffraction grating. It's really just a 2-slit diffraction grating. And it produces a pattern. I showed y'all with the laser where we had a really central bright spot, and then the spots on the side were dimmer and dimmer. And that's what this represents. This is like an intensity graph, but flipped on its side. So this has a big intensity, smaller intensity, smaller intensity. I wanted to know the distance on the screen from that central bright spot to the second bright spot. I wanted to know this distance, which is y. That's going to be, I draw a triangle here, because I can calculate this angle theta. That's d sine theta equals m lambda. And that was our first step, was to calculate that angle theta. This is a distance L. Since tan theta is y over L, I can calculate y. That's where that comes from. That equation is on your worksheet, but you need to know, on your equation sheet, but you do need to know sort of how to use it. What is y, what is L, how to find theta. Does that help? Okay. All right. So that's that one. So knowing how to do that one will really help you on the multiple choice. And then you will have a lens or mirror that you have to draw the rays for. This one, you only have to draw 2 rays. Honestly, I just draw the easiest rays that you can. I think parallel to the axis right here, and then through the focal point. Remember, this is a diverging mirror though, so that ray is going to go back like that, as if it's coming out of the focal point. So notice how I did that, I drew a line that went back to the focal point, and then the reflected ray is collinear with that line. It's in the same line. So then I can trace that back to find where the ray is. I think for the mirrors, another really easy one is just to the center of the mirror, and then follow the law of reflection. And then I can trace that back. And where the image is right here. So my image is right there. I only need 2 rays. Don't draw 3 or 4. Just draw 2. It makes it a lot easier for me to see. And then please just draw 2 rays. Because if one of them's wrong, I'm probably going to use it as the one that you draw. And then I want you to describe the image. This is a real or virtual image. It's virtual. Upright images are always virtual. And it is smaller than the object. Okay? Be able to do that for all 8 scenarios. any one of those 8 scenarios. But knowing, don't look at that, look. All right, all 8, okay? But knowing them will really help you on the multiple choice, because you're going to have questions in the multiple choice that ask you, one, which of these rays are correct or incorrect, and then also which images are formed in which scenarios. Those will be, those skills that you do, that you build, knowing how to draw the ray diagrams, will help you on 5, 6, 7 of the questions on the multiple choice. Okay? Know the free response, and then also in the course of that, know the ray diagrams. I'm not going to give you the no images, so there, that turns it down to 6. You only need to know 6. Does that help? Well, y'all look unhappy. Are you unhappy? Sorry. Okay. So those are the free response. Make sure you know those cold. You need to know them very well. Particular questions for the multiple choice. Oh, we had an exam. We had chapter 6 in this spring 22. So you will not see stuff from chapter 6. We did that in the last exam. Lenses and mirrors, and then interference of light. Particular questions, y'all? On this exam, spring 22? Sure. Okay. Yeah, so we saw this in the concept test. Those are on Canvas, by the way. I want to know what factor is the distance changed when the distance between the slits is doubled. So this distance is d. The distance that we're talking about here is y, right? So this distance is the distance between the slits. And I want to know the distance between adjacent bright and dark spots. I'll just say, what is the distance from here to here, y? So d sine theta is equal to m times lambda. When I double this distance, then that will have the angle. If the distance d goes up, the angle is going to go down. And then I say y is equal to L tan theta. If this goes down by a half, the angle, look, I get the sine and the tans. We're assuming small angles, so we'll just assume whatever happens to theta will also happen to sine and the tan, okay? So if that goes down by a half, then the distance between the adjacent light and dark fringes is also halved. So C is the right answer there. It goes down by a factor of a half. Okay? You're going to see others of these, by the way. These are all students that I've had in the past. Lillian is a vet now. Angel, I think she's a doctor. Yeah, she's a doctor. William Robichaud, he's a... I'm remembering these students. Can we have just a second? Will Robichaud, he's like a researcher out at he's up in Boston somewhere. He has a wife. And then Lindsay, y'all know Lindsay Lassane. She's a neurosurgeon here, right? What is it? 15? Yeah. I'm talking about those. They were good students. Lindsay was like 16 when she came into physics. Y'all know Lindsay Lassane? Yeah. 15? Yeah. A double slit has a slit width d of 1 times 10 to the minus 6, or 1 micron. Light of wavelength, 370 nanometers, or 370 times 10 to the minus 9 meters. Is this on a double slit? I want to know how many bright spots there are on the screen. So remember, when I'm asking this, we're assuming then that theta is equal to 90 degrees. Because when theta is 90 degrees, that's the maximum angle that you can have for that light coming off of the double slit and still give you interference patterns. It's like a theoretical maximum. You can't go beyond 90 because then the light would be going behind the screen. So I'm going to let theta equal to 90, and I say d sine theta is equal to m lambda. I'm looking here for m. I'm trying to solve for m. The sine of 90 is equal to 1. So m is equal to d divided by lambda. And if I do d divided by lambda, I get 1 times 10 to the minus 6. I get 2.7. So you might be inclined to put 3, but that would be wrong. Let's look at our interference pattern. What that means is that I get 2 bright spots on either side. I can't round this up, even if it's 2.9. I don't round it because that means that I haven't yet gotten to that next bright spot on the interference pattern. I have a first order here, and I have a second order. I don't have a third order. I'm almost there, but not quite a third order. So if I'm asking for the number of bright spots on the screen, like the bright spots that I showed on the board last time with the laser and the diffraction grating, I would have a central maximum, and then I'd have a first order and a second order, and then another first order and another second order. So I'd have a total of 5 bright spots on that interference pattern. Okay? Sydney? That's good. You're going to see a problem like that, of course. They're on all the exams, so you'll do it. And you'll get it just right on Monday. Right? Calculate M, don't round it up, double it, and add 1. Draw a picture. Picture always helps me think about it. It'll help you, too, to think about it. Don't round up. You can't have 0.9 kids. And double it, and add 1. Other particular questions? Juliana? Ian?
Is there any way you can like recap like every like mirror or lens and like the images?
Yeah. Mm-hmm.
And like convergent and divergent?
Yeah. So a good way to think about it is think of them as converging and diverging devices because they're going to be really similar. So converging and diverging. In converging, for mirrors, that would be concave mirrors. For lenses, it's going to be convex lenses. For diverging, that is convex mirrors and concave lenses. Okay? But think of 2 big categories, converging and diverging. For the concave mirrors, there are 3 scenarios. My object can be outside the focal point, at the focal point, or inside the focal point. That's my object. My image, if it's inside the focal point, will be inverted and real. Bigger, smaller, same size, it depends where the object is. This image will have no image at all. In fact, we'll find that Q is equal to infinity for that, if F is equal to P. And here, I get an image that is upright, virtual, and big. Right? It's like your makeup mirror. That's your makeup mirror. So that's concave mirrors. Convex lenses, we'll find that have the same descriptors. It's just that we're written a little bit differently. But my object can be outside the focal point, at the focal point, or inside the focal point. Here, my images would look a lot the same. Inverted, real, no image, virtual, upright, and bigger. So the same words that I wrote up here will also fall down here. It's just where I draw the images looks a little bit different because for lenses, the real side is opposite the object. The virtual side is the same side as the object. But for mirrors, the real side was the same side as the object, and the virtual side was the opposite side of the object. That trips up students a little bit. Let me repeat what I just said. For lenses, the real side is opposite the object. The virtual side is the same side as the object, but it's different for mirrors. For mirrors, the real side is the same side as the object. The virtual side is the opposite side of the object. In the notes, you have a similar figure to this, okay? But it's useful to think about them in terms of converging devices because they do the same things to the light. For diverging devices, that would be a convex mirror or a concave lens. The object is here, object is here. At the focal point, it doesn't matter. And then the image is here. The image is here. Okay? That is a virtual, upright, smaller image. It's like a security mirror. Virtual, upright, and smaller. Knowing those will help you. They'll help you too with array diagrams, or the array diagrams will help you understand those too. Right? Yeah. They're both virtual, upright, and smaller. Yeah, that's a good summary of what they all do. Okay?
Can you repeat what you said one more time about, you said lens, the real side is the opposite side of the object?
Yeah, so for lens, let me write it. For lenses, this is where you get real images. This is where you get virtual images. Same, opposite the object, same side as the object. For us, we'll always have the object on the left-hand side of the lens or mirror. Okay, that's always, the light is always coming from the left. For mirrors, the real side is the same side as the object. Notice that's different from lenses. And the virtual side is right here. It's opposite the side of the object. So notice here our virtual images. Our virtual image is the opposite side of the object for mirrors, the same side of the object as lenses. The virtuals, they flip sides between lenses and mirrors. It's because the lenses refract light and the mirrors reflect light. So the virtual side is opposite the side on the mirror. Okay? Ever seen that movie Poltergeist from the 1980s? Where people are like living in the mirror? Have you seen it? It's a bad movie. Anyway, like the people, like those mirror people, they live in the virtual side. They're virtual. Yeah, you see it? You see it? No? Okay. Ian, you have a question?
Can you do 14 on the 22?
Yeah. Okay, so if I move the screen further away, what happens to the central bright spot? Imagine my diffraction grating, I draw as a double slit, and you have this light that produces, or imagine the angle theta, that I have that angle theta. That angle theta right there that describes the size of the central bright spot. And so if I move my screen farther away, best way to think about this, move my screen farther away, just imagine this light ray extending out farther. So what's going to happen to the central bright spot? It gets wider, right. The same is true, like if I have a piece of paper and a flashlight, and I just move the paper farther away, the spot on the paper is going to get bigger. So this question isn't really about the diffraction pattern. It's really about what happens when you move the screen away. If you want to think about it from the math perspective, that y is equal to L tan theta. If L goes up, y also goes up. And y describes the size of the bright spot. So you can think about it that way too. Okay? Questions? Listen, I know you have a lot going on. Like you probably have other exams on Monday. Did you organic on Monday? Yeah. Get lots of sleep this weekend. Okay? It's very important that you come in well rested. You don't believe me, do you? It's very important that you come in well rested. Other questions? No? Huh? 19? All right, we have y'all hang tight, okay? We have a few more questions. 19. Okay, you're going to see one like this. All right, we had one in class. I have, the important thing here is the path length difference. I have two paths that are traveling. One travels 3 meters, the other travels 4 meters. So the path length difference is 1 meter. The other thing that's important is the wavelength. The wavelength is equal to 2 meters. Then the important thing is what value of wavelength is the path length difference. The path length difference is 1/2 of the wavelength. So these two waves are offset by 1/2 a wavelength. What happens when I have an offset of 1/2 a wavelength? That is constructive or destructive? It's destructive. If you were going to express it in degrees, it would be 180. Right, very good. So that's destructive interference, or 180 degrees out of phase. Destructive interference gives me a dark spot. Okay? Sydney, do you have a question too? Okay. You're going to see one like that. Okay? And it'll be simple numbers like that. You just have to know what is the path length difference, what is the wavelength. If it's 1 wavelength, I get a bright spot. If it's 1/2 a wavelength, I get a dark spot. If it's somewhere in between, I get what I call a gray spot. Something that's neither bright nor dark. In between. Something between 1 and 1/2. Or, not, it could be 1, 2, 3, 4 wavelengths. It could be 1/2, 1 1/2, 2 1/2. But if it's 1 3/4, that's a gray spot. Okay? Okay. If it's 1 wavelength, 2 wavelengths, 3 wavelengths, dark spots. Bright spots. 1, 2, 3, bright spots. If it's 1/2, 1 1/2, 2 1/2, 3 1/2, dark spots. If it's anything else, it's a gray spot. Okay. All right. I think you're making me a little nervous looking at you because